Welcome to the pod, Cultivating Innovation, one batch at a time. This is biomanufacturing and fermentation technology.
Welcome back to the deep dive. We're here to take those dense stacks of articles, notes, and research, the kind of stuff you feel like you should read but just never have the time for, and distill them into the most powerful, memorable nuggets of insight.
And today, we are really bridging two massive, complex fields, chemistry and, well, living biology.
The subject is biocatalysis, but we're taking the conversation out of that sterile, predictable test tube.
That's exactly right. When most people hear biocatalysis, they picture a highly purified enzyme working beautifully in a controlled buffer.
Clean, simple, predictable.
Right. But our deep dive today focuses on what happens when chemical transformations are executed inside a living, breathing, adaptive cell. A whole cell biotransformation.
And that's a completely different ballgame.
It's a fundamentally different regime. The sources we've analyzed consistently argue that the cell is not just a passive container for your expensive enzyme. It's a structured, adaptive, and transport-limited material.
A material, that's an interesting way to put it.
It is. Because its internal physiology actively dictates the reaction's kinetics, its selectivity, its robustness, and critically, whether the process can ever actually work at an industrial scale.
So our mission today is to really understand the cell itself as a kind of reactor, not just the enzyme that happens to be inside it. And to do that, we have to tackle this fundamental conflict, right? The cell provides this incredible intrinsic help.
But in doing so, it imposes enormous complexity and constraint.
Exactly. So let's start with the history. If we have isolated enzymes, why did chemists even look toward using intact whole cells in the first place?
Well, it was initially a massive trade-off, and it was driven almost entirely by practicality and economics. You're right that the cell offers help, but that help solves a few problems that were just huge historical bottlenecks.
Especially for certain types of chemistry.
Especially for redox chemistry, which is really the backbone of so many synthesis routes. Intact microbial cells offered two immediate, immense advantages for industry.
Okay, what are those two?
First, they intrinsically provided cofactor regeneration.
Okay, so things like NADPH.
Exactly. Those cofactors are consumed in stoichiometric amounts by the reaction. You need a massive continuous supply or, a cheap way to recycle them.
And the living cell is basically a perpetual self-sustaining recycling machine for them.
It's perfect for that. And second, using the whole cell eliminated the extremely costly, time-consuming, and scale-limiting step of enzyme purification.
So you don't have to spend millions trying to get one protein perfectly pure.
Why would you when you can just use the whole organism that made it for you for free?
So the original rationale was essentially a cost reduction shortcut. You bypass the complex purification and you get a free, built-in continuous power supply for your reaction.
That makes perfect sense for making that jump from the lab bench to the industrial fermenter.
It does. But this is where that core conceptual distinction you mentioned comes in.
It is. Because purified enzymes operate in a fully engineerable environment. You control the pH, the temperature, the exact concentration of every single molecule. Total control. But whole cell catalysis embeds that exact same chemical reaction within this complex, living, regulated network. You've got metabolism, membranes, homeostasis.
The cell is constantly trying to keep itself in balance.
Constantly. It's regulating, adapting, transporting. Which means the cell itself becomes a dynamic, active part of the catalytic mechanism.
So it's not a jar, it's a living reactor material.
That's the reframe. We're moving from a passive, controlled vessel to an active, regulated, dynamic material.
Okay, so if the cell is truly this dynamic reaction matrix, let's unpack that. What specific elements turn this potential free helper into what is, in reality, a fundamentally complex and constrained system?
All right, so first we have to define the functional boundaries. It's important to remember that whole cell and cell-free systems can often execute the same net chemistry. They're both driven by the same enzyme at their core.
But the difference is how you control it.
The divergence is all in the nature of control. When you use a cell-free system, you have direct granular control over everything.
You're setting the pH, the exact ratio of substrate to enzyme, the medium composition, down to the millimolar level.
Precisely. Now, when you choose the whole cell route, you control physiology and mass transfer, but you do it indirectly.
How so?
You're manipulating the system through these bulk parameters. The set points on the bioreactor, the nutrient feeds, the oxygen supply rate, and managing the cell's growth state.
So you're managing the factory by managing the factory's environment. not by replacing the individual cogs inside.
That's a great way to put it.
But if control is so much harder in whole cell systems, there must be situations where the biomass confers such an intrinsic advantage that it's still the superior choice. I mean, where is that sweet spot?
The sweet spot is always where the cell solves an economic or technical problem that is just prohibitively expensive or complex to solve in a cell-free environment.
And we come back to those cofactors.
It almost always centers on cofactor-dependent reactions and the need for continuous, low-cost cofactor regeneration. Think about something like whole-cell reductive amination.
A process used to make valuable chiral amines, right, for pharmaceuticals and things.
Exactly. Reductive amination requires a continuous supply of NADPH. In a cell-free system, you'd have to buy and add that expensive cofactor.
And then you'd have to buy and add another enzyme just to regenerate that cofactor after it gets used up. That's 2 extra expenses right there.
2 big ones. But the intrinsic cellular dehydrogenase activity can continuously recycle the required cofactor, supporting cost-efficient operation. You avoid that whole separate enzyme regeneration system.
That's the intrinsic advantage.
It is. And what's more, this intrinsic help enables really complex multi-step transformations. If you need to convert compound AD, and that requires intermediates B and C.
The cell's native metabolism can supply all the necessary redox equivalents or intermediates for the entire cascade.
All within a single, highly organized living system.
So the cell acts as this metabolic integration platform, solving multiple chemical problems at once. But that complexity has to come at a price.
And the price of that intrinsic help is regulatory complexity. The moment you rely on the cell's structure, you introduce hard constraints.
Like what?
Transport limitations, for one, just getting the molecule in and out of the cell. And then competing metabolism, the cell, using your substrate for its own purposes.
So it can become rate limiting or even degrade your product.
Absolutely. And this is the fundamental trade-off. Is the cell's metabolic context helpful by providing that redox fuel? Or is it harmful by diverting or destroying your substrate or product?
And the choice of which route to take often comes down to which side of that ledger weighs heavier for a specific chemical transformation.
Exactly.
Okay, so we've established the cell is a structured material, and a key benefit of that structure is compartmentalization. It localizes enzymes, maintains these separate dense cofactor pools.
It does.
But you can't have compartmentalization without creating a wall. And a wall, by definition, limits flow.
And that's the constraint. Diffusion and transport limitations. If you're trying to make some novel pharmaceutical intermediate, the substrate is probably non-native to the cell.
The cell has never seen it before.
Right. So the necessary uptake of this non-natural substrate and then the export of the non-natural product become the primary hurdles. The literature repeatedly stresses that transport is a first-order determinant of apparent activity.
A first-order determinant. So it doesn't matter how great your enzyme is.
It doesn't matter if your target enzyme has been super-engineered for maximum turnover. If the substrate takes 10 minutes to cross the membrane, the apparent rate of your reaction will be 10 minutes.
The rate is capped by the envelope, not the enzyme inside. But even once the substrate gets in, the kinetics we measure in a clean buffer, they still don't apply, do they? That internal environment is far from ideal.
Not at all. That's due to significant microenvironment effects. The inside of a cell is closer to a dense gel than a dilute solution.
So it's crowded.
Very crowded. And you have factors like local intracellular pH, the overall redox state, which is constantly fluctuating, and just the sheer density of metabolite competition. All of this fundamentally shifts the apparent mechanism.
And that can change things like the apparent Km.
It can dramatically change the apparent Km and the substrate concentration needed to reach half maximum rate, or alter how a product inhibits the enzyme. In a test tube, you might find your enzyme works best at pH 7.5.
But inside the cell, who knows?
Inside the cell, the local enzyme environment might be pH 7.2 and packed with competing sugars. Isolated enzyme kinetics simply do not translate directly to the cellular context.
Okay, and this is where it gets really interesting, because this is the crux of the industrial challenge.
Yeah.
If the cell is this dense, constantly regulated microenvironment, how does that environment react when you try to scale it up into a vessel the size of a small house?
This is the scale amplification problem. Industrial reality introduces profound heterogeneity. You simply cannot perfectly mix a 100,000-liter bioreactor.
Not perfectly, no.
And that imperfect mixing creates time-varying redox states and microgradients. So even if the bulk set points, the average dissolved oxygen, the bulk pH remains stable on your monitor.
The individual cells are experiencing something very different.
The individual cells are circulating rapidly through zones of high oxygen, high substrate, and then low substrate.
So the cell isn't sitting in a stable environment, it's experiencing these rapid, repeated shocks.
Exactly. This heterogeneity imposes repeated, rapid shifts in local oxygen or substrate concentration, which directly influences catalytic output, especially for those highly sensitive redox-driven biotransformations.
And I imagine that stresses the cell out.
Immensely. It forces the cell to consume energy for maintenance and adaptation rather than for your desired chemical conversion. We've turned a smooth, lab-scale reaction into a stressful, turbulent journey for the catalyst.
To try and manage this trade-off between the intrinsic help and the structural constraints, engineers have developed different operational philosophies for the cell biomass itself. Let's define the three main modes. First up, we have living cells.
Right, so living cells are growing and actively adapting. This provides the maximum capacity for energy generation, self-repair, and robust cofactor regeneration.
So they're strong, they're resilient.
Very. However, the major operational risk is physiological drift.
Meaning the cell changes its mind about what it wants to do.
In a way, yes. The cell changes its metabolic priorities over time, maybe by mutating or just shifting its flux allocation. This can lead to decreased yield or the formation of unwanted byproducts as the cell tries to maximize its own growth instead of your product formation.
So there's an inherent conflict between growth and production, which leads us to the next mode, resting cells.
Resting cells operate under minimal net growth. You're essentially putting the cell on a controlled diet so it focuses only on the catalysis.
How do you do that?
It's often achieved by limiting a key nutrient, like nitrogen, or by running the conversion after the main growth phase is over.
And the upside there is improved selectivity and simplified control, because you've taken that growth objective off the table.
Precisely. You've decoupled the two processes. But the trade-off is you have reduced self-repair capability and sometimes a reduced capacity for complex long-term cofactor regeneration.
Because the energy required for basic maintenance is just declining.
Exactly. The cell is no longer building, it's conserving.
And finally, the most radical approach, permeabilized cells.
With permeabilized cells, you're intentionally weakening the transport barriers, usually with chemical agents like detergents or specific physical treatments.
This is a direct attack on that number one constraint we talked about, transport limitation.
It is. You're trying to expose the intracellular catalyst directly to the substrate, and the rate goes up, but the price is steep.
What's the major risk here? What's the downside?
You significantly increase the cell's vulnerability to external toxicity, and critically, you risk cofactor leakage.
So the very thing you're trying to take advantage of.
If those expensive cofactors like NADPH bleed out of the now compromised cell envelope, you lose the primary economic benefit of using the whole cell in the first place, and the robustness of the system just collapses.
That distinction between resting and passive seems really important here. When we say resting, it sounds like the cell is asleep, but the sources make it clear that even non-growth conversions still have energy demands.
That is an essential mechanistic insight that process engineers can sometimes miss. Resting does not mean zero energy required.
It's not off, it's just idling.
Right. And specific studies on whole cell oxygenase biocatalysis demonstrate that NADH availability can still limit the catalytic rate, even when the cells are carbon limited and not growing.
So even when it's resting, it's still burning fuel.
The cell still requires energy for basic maintenance, motility, survival. Its energy charge has to be sustained. This shows that engineered redox supply is necessary even when the cell isn't growing. The conversion rate is still fundamentally bound by the cell's internal finite energy budget.
Okay, let's drill down now into those microscopic barriers. You've stressed that transport limitation is the most common and difficult reason why whole cell rates fail to match the expectations we set with purified enzymes.
It really is. The substrate has to first cross the cell envelope, and then once it's inside, it has to compete with the cell's own massive concentration of native metabolites just for access to the target enzyme.
It's a traffic jam at the door, and then once you're inside, it's like a packed subway car. For non-natural substrates, the cell may not have any natural mechanism to bring the molecule across the membrane. So how do researchers force the system to accept these non-native molecules?
For industrial practicality, you have to engineer the system around this problem. This often means expressing specific transport genes.
So you borrow pumps or porins from other organisms.
Exactly. You insert them into the host cell to specifically shuttle the substrate or product across that membrane barrier. Or sometimes it requires engineering alternative host organisms that naturally have a more permeable cell envelope or maybe lack certain afflux pumps that would just kick your product right back out.
So solving the transport problem is often more critical than improving the enzyme itself.
In many cases, absolutely. Transport is the gatekeeper. And once that gate is breached, you face the next problem: metabolite competition, or crosstalk.
Okay, what's crosstalk?
This happens because engineered pathways often rely on molecules that are also crucial intermediates in native metabolism. A shared intermediate, intended for your synthetic chemistry, can be quickly siphoned off into cell functions,
Like growth or energy production?
or the synthesis of completely different native molecules. And this drastically reduces the effective substrate availability for your desired reaction.
And that's the silent killer you mentioned earlier. If the cell is constantly diverting, say, 5% of the substrate to make its own amino acids, how does that translate to an industrial failure mode?
It's a crucial industrial failure mode because those small diversion fluxes only become catastrophic at scale. In a 5-liter flask, that 5% might be negligible. You might not even notice it.
But in a 50,000-liter reactor running for 2 weeks,
Those small, persistent losses integrated over time and scale translate into massive yield losses and economic disaster. It highlights a key lesson. The cell always prioritizes its own survival and maintenance over your product yield. You have to actively fight its natural instincts.
okay, so if the enzyme is the machine, the cofactor is the fuel. We know native cofactor recycling, that NADPH, is the primary economic justification for using the whole cell. It's the intrinsic catalytic asset.
That's the ideal case, yes. The reality is that this cellular power source has a finite capacity, and it operates under immense pressure. When your engineered reaction demands high flux, the cell's internal redox pressure and its overall energy charge can become limiting factors very, very quickly.
Let's use that epoxidation example again to make this tangible for everyone.
Okay. So we have quantitative experimental evidence that demonstrates that NADH availability can cap whole cell epoxidation rates even when you are supplying enough oxygen and substrate in the bulk medium.
So it's not the raw materials.
No. What this tells us is profound. The bottleneck isn't the environment outside the cell, or even the enzyme itself. The bottleneck is the cell's internal energy supply line. Intracellular redox state is a quantitative hard constraint that you have to engineer around.
And if you demand too much from that power source, you introduce what's known as metabolic burden.
Yes, high flux demand triggers a stress response. The cell responds by shifting its metabolism, which often leads to overflow byproducts.
The classic example being acetate formation in E. coli.
That's the one. The cell is effectively dumping excess carbon and energy because it can't process it efficiently under stress. And this formation of unwanted byproducts severely reduces your overall catalytic capacity and adds a huge expense to downstream purification.
And again, this burden isn't static. It's dynamically amplified when you scale up.
Precisely. That mixing heterogeneity in large-scale operations means cells are exposed to rapidly fluctuating oxygen and substrate levels, pushing them into these stress cycles over and over. This creates rapidly fluctuating redox states, further destabilizing conversion performance, and driving the cell to waste energy producing non-productive overflow metabolites.
The problem with using a biological system for chemistry, it seems, is that the desired product is structurally and chemically similar to the molecules the cell uses every day.
To the cell, your valuable intermediate is just another metabolite.
So it's going to try and use it.
If you don't insulate it, export it, or produce the product in a form the cell cannot readily consume, competing pathways and product degradation are an endemic structural risk.
It's like hiding a valuable package in a shared kitchen. Eventually, someone is going to use it for something else, or maybe just degrade it. What are the key strategies for building that protective barrier around the desired product?
The primary strategy is multifaceted metabolic engineering. In cases like whole cell reductive amination, strategies include flux redirection, so actively suppressing competing native pathways that might consume your intermediates, and precise tuning of cofactor regeneration.
For instance, you might need to amplify the pathway that specifically regenerates NADPH while minimizing the pathways that rely on NADH.
Exactly, based on the specific requirements of your synthetic enzyme.
So it's not just about turning on the new enzyme. It's about strategically turning off the old competing enzymes. But you need to know exactly which switches to flip.
And that's the persistent knowledge gap. We lack truly predictive models for identifying this crosstalk under real process conditions. Native pathway activity isn't constant. It shifts dynamically based on subtle factors like nutrient limitation, oxygen availability, and general stress.
Conditions that are common in manufacturing, but often deliberately eliminated in idealized lab experiments.
Which means we often don't discover the costly crosstalk until we're already trying to scale up.
Okay, let's move into reaction engineering. We have to address the reality that many high-value chemical targets, things like complex molecules, solvents, drug precursors, are hydrophobic. They don't mix well with the cell's watery environment.
Right, and this necessitates biphasic or multi-phase operation. You're using both an aqueous phase where the cells live and an organic phase to dissolve the substrate.
On the surface, that seems like a brilliant solution. The organic phase acts as this massive reservoir, dramatically increasing the overall concentration of a poorly soluble substrate in your reactor.
It does solve the solubility problem, but it introduces massive complications for the living material. Here's the aha moment that often breaks industrial processes. The organic phase creates local concentration spikes at the cell surface.
Wait, why? Doesn't the organic phase just sit separate from the aqueous phase?
In a reactor, it doesn't. The organic phase is dispersed as millions of tiny droplets, creating a massive interfacial area. Substrates partition into the organic phase, but they must transfer across that interface and dissolve into the aqueous phase before the cell can take them up.
But at the moment of contact.
At the moment of contact between an organic droplet and the cell membrane, the membrane experiences a highly concentrated, localized exposure to the hydrophobic substrate.
So the cell membrane, which is itself made of lipids, is being directly challenged by high concentrations of these hydrophobic molecules dissolved in the organic droplet.
Exactly. And this causes the cell to experience apparent toxicity thresholds that are far, far lower than you would expect based on the calculation of the overall bulk concentration in the reactor.
Because the toxicity is a microgradient problem, not just a total concentration problem.
It's an engineering problem of microgradients. And this means that for large-scale multi-phase operations, the reactor configuration itself becomes a state variable.
So it's not just chemistry anymore.
Not at all. At manufacturing scale, 3 critical intertwined state variables emerge that you don't really deal with in single-phase systems. The interfacial area between the phases, the droplet size distribution of the organic solvent, and the mixing time of the whole system.
So you need enough mixing to transfer the substrate, but not so much that you create damaging shear forces or expose the cells to overly aggressive organic droplets.
It's an incredibly delicate balance. Multi-phase whole cell transformations are orders of magnitude more sensitive to the precise reactor configuration than standard aqueous systems are.
Okay, let's talk about the biological consequences of that exposure. When the substrate or product hits the cell, what are the core mechanisms of toxicity?
The primary mechanisms involve membrane disruption. The hydrophobic molecules interfere with the lipid bilayer, which leads to leakage of internal components, and the induction of a massive redox imbalance.
So the cell is suddenly overwhelmed and has to drain its energy reserves trying to pump out the toxic molecule or just repair the damage.
Exactly, and this damage doesn't require cell death to destroy your productivity.
No, even subtoxic levels can be a problem.
Crucially, yes. Even subtoxic levels can severely limit catalytic capacity by forcing the cell to increase its maintenance energy requirements. The energy that should have gone toward converting substrate into product is now diverted to survival and repair.
I think you mentioned a specific study on this.
Yes, in studies of recombinant whole cell epoxidation, researchers found that subtoxic levels of the product limited the overall epoxidation capacity. The cell was spending all its energy cleaning up the product instead of making more of it.
That sounds like a perpetual treadmill, and it leads to what you call productivity drift.
That's the result. Stress-induced variability causes productivity drift because the cell adapts to this constant low level of force. This adaptation includes changing its membrane composition to become less permeable, altering its transporter expression and reallocating metabolic flux.
And that drift alters the apparent selectivity and kinetics over time.
So a process designed in week 1 is completely different by week 4 of a continuous campaign.
And we keep coming back to the large-scale driver, heterogeneity.
Yes. The mixing heterogeneity in large reactors means cells are constantly experiencing these rapid, severe excursions in oxygen and substrate levels, which accelerates this physiological drift. Every time the cell cycles through a low oxygen zone or hits a high substrate spike near an organic droplet, it adapts. And that adaptation pushes the entire population further away from the optimal catalytic phenotype you established in the lab.
So if we look at the kinetics from an engineering perspective, the conclusion seems to be that in whole cell systems, the apparent reaction rate is a composite rate.
It's a messy function. It conflates the intrinsic enzyme kinetics with the efficiency of transport, the current metabolic state, and the level of internal inhibition.
So the intrinsic parameters, the Kcat and Km that you measured for your isolated enzyme in a clean buffer, are essentially non-identifiable in the whole cell system. You can't tell if a reduced rate is due to a slow enzyme or a slow membrane.
You really can't separate them unless you independently measure or specifically constrain the transport and the cofactor supply. And this composite nature of the rate is further complicated because the cell's growth state profoundly modulates the kinetics.
How does the growth state modulate it?
Well, whether the cell is actively growing or resting dictates its cofactor generation capacity, its maintenance energy demand, and the volume of competing metabolic fluxes. An actively growing cell has massive energy generation capacity, but also huge competing demands for biomass synthesis.
Whereas a resting cell?
A resting cell has lower competing demands, but also less overall capacity. This explains the classic dilemma. Resting cell conversions often show improved selectivity, so less byproduct formation, but they risk greatly reduced robustness if the underlying engineered redox supply fails during the long conversion phase.
So the cell's internal environment acts like a constantly shifting resistor in the catalytic circuit. You can measure the total current, which is the apparent rate, but you can't isolate the intrinsic resistance of the catalyst from the variable resistance of the power supply and the wiring.
That analogy perfectly captures the complexity. The process engineer is trying to run a steady current through a circuit where the resistance is constantly changing based on environmental factors the cell is attempting to respond to.
Let's examine how these insights shape industrial practice, starting with growing cell biotransformations. The key advantage here is that coupling product and biomass formation increases overall robustness. The cell can self-repair, sustain high-capacity cofactor regeneration.
It can, but as you noted, the objectives conflict. The cell wants to grow quickly, the engineer wants it to channel energy toward making an expensive product efficiently, and this conflict is amplified under the oxygen transfer limits inherent in large vessels.
That's the central control conflict. How do they manage this?
Industrial operation relies heavily on sophisticated control logic, usually substrate-limited fed-batch logic. This means they starve the cell, but just enough.
Why starve it? What's the benefit of that?
Starving the cell, or keeping the substrate concentration just above the limiting level, is critical for maintaining respiratory balance. And crucially, it helps avoid the formation of overflow byproducts like acetate.
Right, which is the cell's way of saying, I have too much sugar and not enough oxygen to burn it efficiently.
And that severely depresses the conversion rate and complicates downstream recovery. Fed-batch logic provides a tighter leash on the cell's tendency to overeat and stress out.
So resting cell systems are the primary response to that growth production conflict. You're specifically aiming to decouple growth from catalysis, which usually improves selectivity and reduces those growth-associated byproducts.
Yes, the focus shifts entirely away from biomass yield and toward maximizing conversion yield and purity. However, the limiting factor shifts entirely as well. You're no longer worried about growth competition.
But you become hypersensitive to maintaining sufficient redox and energy supply and maximizing toxicity tolerance during that extended conversion phase.
Exactly. Which brings us back yet again to the energy source. You've decoupled growth, but you haven't decoupled the energy requirements.
And we see experimental findings confirming that even when carbon limited, NADH availability can still limit whole cell epoxidation.
Which emphasizes that simply stopping the feed isn't enough. The process needs a highly engineered capacity for continuous, sustained, low-demand redox supply. You have to design a bespoke energy system for the resting cell that is highly efficient and resilient.
A completely different approach involves making the cell itself part of a fixed structure, immobilized and structured biomass systems. So we're talking about encapsulated cells, carrier-bound cells, or biofilms.
Right, and this is often done to align the cell catalyst with the logic of continuous processing for stability and reuse.
So immobilization fundamentally changes the reactor design.
It does. It provides long-lasting stability, especially when you co-immobilize the whole cells with other necessary components or chemical catalysts. This makes continuous flow operation, which is highly desirable for cost efficiency, far more practical than using free cell suspensions.
So what's the trade-off for gaining that massive stability and reusability? It sounds almost too good to be true.
It introduces the same fundamental constraint we discussed, but in a highly intensified form. The structured environment that stabilizes the cell adds significant new diffusion barriers.
So you solve one problem and create another.
Local inhibition and toxicity inside the carriers, where the cells are packed tightly together, can intensify transport limitations exponentially. This is a crucial scale-dependent risk because diffusion limitations become far more consequential as the size of the immobilized carrier and the overall reactor volume increase. The diffusion bottleneck goes from the single-cell membrane to the entire carrier surface.
Okay, so let's talk about the reaction classes where this whole cell approach really shines.
The canonical domain, where a whole cell biocatalysis truly excels, is redox biotransformations. This includes the highly selective synthesis of chiral alcohols, ketones, aldehydes, and amines.
And this success is built entirely on that economic argument. The intracellular redox metabolism and cofactor recycling.
Precisely. Whole cell reductive amination is a perfect case study. It demonstrates how the system exploits intrinsic cellular enzymes for regeneration, dramatically reducing the need for external, non-reusable materials. However, this success is managed under the shadow of a critical constraint, the redox budget constraint.
Let's elaborate on that using a financial analogy as we planned. If the cell is a small company, what does this budget constraint mean for industrial design?
Okay, so imagine the cell's total NADH and ADPH production as its cash flow. This cash flow has to simultaneously cover three distinct costs. You have the conversion cost, the direct stoichiometric demand of your reaction.
The cost of goods sold, basically.
Exactly. Then you have the maintenance cost keeping the lights on, basic survival, and finally, the stress costs, the emergency fund needed to adapt to changing environments, pump out toxins, and repair damage.
And that cash flow is finite.
It's finite. So the industrial design constraint is that whole cell redox biotransformations must be designed around this total redox budget. If the chemical flux demands too much cash, the maintenance and stress costs are unmet, the enterprise collapses, and productivity drops to zero. Industrial stability means operating well below the maximum cash flow to ensure that emergency fund is always available.
Moving beyond simple redox, how does the cell enable the assembly of more complex molecular structures, like CC bond formation?
These reactions, which include things like aldol condensations, carboxylation, and hydroxylation, rely heavily on the metabolic context as an enabling factor.
What does that mean, enabling factor?
It means they're feasible because the cell supplies necessary reactive equivalents, specific activated molecules or cofactors that are really difficult to generate chemically. Furthermore, the cell's internal structure, through coupled pathways or compartmentalization, can stabilize highly reactive intermediates that would immediately degrade in an open, non-biological reactor.
So the cell provides not just the catalyst, but the protected, highly regulated infrastructure for the entire synthesis.
Correct. But this enabling factor is also the source of the ultimate crosstalk risk. The very metabolic context that enables the reaction can also consume the intermediates or degrade the products. Achieving industrial yields frequently requires detailed flux redirection and the active suppression of competing fluxes to prevent the siphoning of those valuable reactive intermediates into native pathways.
One area where enzymes are transforming the pharmaceutical industry is late-stage functionalization, or LSF. What is LSF, and why is the cellular environment so valuable here?
LSF involves taking a nearly complete, complex drug molecule and making one final, highly specific chemical modification like adding a hydroxyl group to one specific carbon atom among 20 others.
So it's like surgical chemistry.
It is, and its value is immense because enzyme selectivity can functionalize these complex scaffolds without the extensive need for traditional protecting group chemistry.
Could you just briefly explain why protecting groups are such an industrial burden?
Certainly. In classical organic synthesis, if you want to perform a reaction on site A, but sites B, C, and D are sensitive, you have to temporarily put a chemical helmet, or protecting group, on B, C, and D. Then you perform the reaction on A, and finally, you must add steps to chemically remove those helmets.
And each one of those steps adds cost, time, and waste.
And, crucially, reduces the overall yield of the process. LSF allows you to skip those steps entirely because the enzyme is so selective it only touches site A.
That's a huge economic advantage. How does the whole cell environment fit into this?
The cellular environment can fine-tune the selectivity, often by modulating the substrate's local availability or microenvironment. However, using whole cells introduces the inherent risks of transport constraints, getting that large, complex drug precursor into the cell, and competing transformations by native enzymes that might degrade your valuable starting material.
So you gain unparalleled selectivity, but you sacrifice certainty and add transport complexity compared to using the isolated enzyme.
It's another one of those fundamental trade-offs.
Given all these pervasive constraints, transport, toxicity, redox limitation, and crosstalk. How does metabolic engineering specifically tackle this to maintain a stable, efficient process?
The primary goal has to be flux redirection and pathway insulation. You're trying to route carbon and reducing equivalents directly to the target transformation while preventing them from leaking into competing sinks.
That's the core objective. And if we look across successful industrial designs, the sources consistently highlight that tuning NADPH regeneration is often the key control point.
Far more important than merely maximizing the expression level of the catalytic enzyme itself. This emphasizes a crucial insight. The supply of energy, the cofactor, is often the limiting factor, not the intrinsic speed of the machine, the enzyme.
That is counterintuitive for a chemist, who usually focuses on the catalyst. It forces us to see the cell as an integrated energy system first. And this control point is what allows engineers to manage that classic tension, balancing growth with production.
Exactly. Growth provides necessary resilience and sustained redox supply, but it consumes resources that could be product. Production maximizes yield, but often stresses the cell. This tension motivates phase-based operation.
A growth phase, then a conversion phase.
A highly controlled growth phase to build a robust catalyst population, followed immediately by a high-flux conversion phase where growth is arrested.
At the industrial level, process control variables are the external levers you use to manage the cell's internal state. So pH, oxygen transfer rate, feeding strategies.
They're paramount because they directly govern the intracellular redox state, the energy charge, and the risk of generating those toxic overflow byproducts.
If the industrial vessels are so heterogeneous, how do engineers monitor the cell's internal metabolic state without constantly taking samples and running complex assays?
They rely heavily on real-time inference using external measurements. The gold standard involves off-gas analytics and ORR, or oxygen uptake rate estimation.
So you're looking at what the cells are breathing out.
By measuring how quickly oxygen is consumed and how much carbon dioxide is produced, engineers can infer the cell's current metabolic rhythm and its oxygen limitation risk. This allows them to precisely control the necessary substrate-limited feeding logic to avoid those disastrous overflow byproducts at massive scale.
But the dynamic nature of these large reactors means that even perfect bulk control isn't enough.
That's the challenge. Since large reactors are fundamentally heterogeneous, stable conversion requires controlling distribution, that is, avoiding extreme and rapid excursions in local oxygen or substrate concentration, rather than just controlling the bulk set points. This industrial reality challenges the academic assumption that the intracellular state remains steady throughout the reactor.
So to the bioreactor, the effective catalyst is not a single uniform entity. It's actually a distribution of phenotypes.
It is. You have subpopulations with varying stress tolerance, different expression levels of your target enzyme, and differing metabolic flux allocations. This population-level heterogeneity can dramatically change the overall reaction outcome.
So long-term reproducibility relies entirely on minimizing the environmental fluctuations that accelerate this physiological drift between subpopulations.
Yes. Reproducibility hinges on preventing repeated stress exposure, those rapid O2 substrate swings, which forces the cell population to adapt and change its performance over time. If your process yield drops off a cliff after a week, it's often because the cell population, not the enzyme, has drifted away from the optimal catalytic state.
Given how dependent we are on the cell's internal metabolic state, what is the major crippling knowledge gap in monitoring these systems?
It's the lack of a predictive mechanistic link between easily measurable online signals like, say, the dynamics of base addition or subtle dissolved oxygen swings, and the population-level catalytic competence.
So we see the symptom, but we don't understand the disease.
Currently, industrial practice often relies on empirical thresholds. If the DO dips below X, conversion drops. We need true predictive models that mechanistically link bioreactor gradients to population stress and resulting flux allocation, moving beyond simple empirical alarms.
Okay, let's take a breath and summarize the non-negotiable benefits that make whole cell biocatalysis worth this immense technical struggle.
The intrinsic benefits are powerful and economic. First, cofactor self-sufficiency, which enable economically attractive redox chemistry. Second, enzyme protection within the cellular environment, which provides greater stability and thermal resistance.
And third, the ability to execute complex, multi-step transformations in a single economical system through the combined functions of native metabolism.
It's cheaper, it's safer for the enzyme, and it's a ready-made platform for complex cascades. Those are powerful arguments.
However, the constraints are equally fundamental and structural.
Transport bottlenecks and metabolic interference are structural properties of living cells, not just artifacts of poor design. The moment you use the cell, you sign up for these issues.
And the practical constraints emerge when we try to leverage those benefits at scale.
Exactly. The scale-up complexity is where the systems often fail, because large reactors impose mixing-driven heterogeneity that triggers stress and overflow behavior, severely reshaping conversion profiles relative to the small-scale lab results. The transition from lab to plant is just not linear.
This leads to a critical industrial realization that optimal operating points are often metastable. What do you mean by metastable?
The industrial reality is that conditions designed to maximize the instantaneous rate, getting the highest yield in the shortest amount of time, often simultaneously accelerate stress and physiological drift.
So they're optimal for a moment, but they reduce the time-integrated productivity, the total campaign yield, over the lifespan of the batch.
Precisely. So industrial optimization, therefore, prioritizes robustness and consistency. You accept a slightly lower instantaneous rate to ensure the cell population remains stable and productive for weeks.
Given this trade-off between intrinsic help and structural constraints, the field is naturally moving toward hybrid solutions that try to bridge that gap.
Yes, like semi-cell-free or permeabilized systems. These are designed to retain the structural benefits of biomass, like internal enzyme stability and some cofactor regeneration, while aggressively relaxing the transport constraints.
So we're keeping the guts of the cell, but making the skin highly porous. What's the unresolved tension when you use this hybrid approach?
The tension is precisely the integrity of that cell wall. Increased permeability solves transport, but it dramatically increases the risk of cofactor bleed, losing those expensive recycled molecules. And it increases the sensitivity to toxicity from external substrates.
So engineers are constantly trying to find that sweet spot, permeable enough to let the substrate in, but robust enough to hold the cofactors inside and resist external shock.
It's a very fine line to walk.
A different trend involves viewing the cell's metabolism not as a nuisance, but as a design space. We're talking about synthetic biology.
Exactly. Synthetic biology treats the entire metabolism as part of the catalytic mechanism.
This sounds like designing a modular factory within the cell itself.
That's the goal. Modular pathway design within the biomass. The aim is to reduce crosstalk by spatially or temporally insulating the engineered pathways from native metabolism, improving flux routing, and ultimately creating truly programmable cellular catalysts.
So if you need an intermediate, you engineer the cell to make just that amount exactly when you need it and shunt it directly to your target enzyme.
That's the dream. But the industrial challenge we discussed earlier, the fluctuating microenvironment, still applies even to the most elegantly designed synthetic circuit. Synthetic biology solves the design problem, but process engineering still has to solve the operating condition problem.
Finally, there's the integration of chemical catalysis with biological systems, chemobiological cascades. This sounds like admitting defeat in the areas where biology is weak and focusing its strengths where it excels.
It is the strategic combination of strengths. These cascades are pursued when a traditional chemical step is necessary to bypass a cellular incompatibility. Perhaps the cell can't survive the high temperature or extreme solvent required for an initial conversion.
So the chemical step handles that, and then the biomass provides the essential, highly selective redox capacity for the later steps.
Exactly. We're splitting the manufacturing process into steps tailored to the tolerance of the catalyst. And physical integration, like co-immobilization of both chemical catalysts, like metal nanoparticles and whole cells, can stabilize the entire cascade.
Which allows for long-lasting, continuous flow processes that are highly efficient and selective.
It's the ultimate realization that the cell is a material with specific exploitable properties, but those properties have hard limits that chemistry can sometimes circumvent.
So what does this all mean for how we approach this field moving forward? The collective evidence forces a massive, necessary conceptual shift.
It means we have to abandon the comforting image of the cell as a passive living factory or an isolated enzyme carrier. We have to instead treat the cell as a reactive matrix.
A complex, adaptive material defined by internal transport limitations, finite redox capacity, and unpredictable adaptive responses.
This framing is essential because it aligns with the operational reality of coupled physiology and reactor gradients. You have to engineer the material properties of the cell itself.
The challenges remaining are daunting, but they seem clearly defined. What are the key knowledge gaps that prevent us from fully mastering this complex chemistry-microbiology interface?
We still critically lack predictive models for transport-limited kinetics and complex multi-phase operations, especially at scale. We need robust methods for quantifying the true redox and maintenance budgets required during long industrial conversions. That financial cash flow we discussed needs a better balance sheet.
And perhaps most difficult.
We need effective strategies for controlling population heterogeneity under the severe, unavoidable fluctuations imposed by industrial scale.
Which gives us the final, practical design imperatives for the next generation of biomass-based systems.
They are threefold. First, we have to aggressively engineer transport and efflux systems to precisely manage substrate availability and product removal. Second, we must proactively engineer the redox supply to sustain conversion without triggering the costly overflow byproducts.
And third?
We have to engineer the reactor and control conditions not for bulk set points, but to minimize gradient-driven stress and the resulting physiological drift.
Ultimately, the question of industrial feasibility is not decided by how fast your enzyme turns over substrate in the lab. It's decided by the stability and long-term competence of the entire living matrix.
Absolutely. The success of whole-cell biocatalysis hinges entirely on whether that biomass matrix can be maintained in a catalytically stable state while managing all the inherent scale-induced complexities over manufacturing time horizons. The future lies in integrated chemistry-microbiology process engineering.
So consider this next time you encounter a molecule synthesized using a whole-cell process.
You are witnessing an entire factory operating at the nanoscale, where humanity relies fundamentally on the internal adaptive engineering of life to perform chemistry we often cannot or cannot afford to replicate in a simple glass flask.
How do we solve the valley of death in biomanufacturing? It starts with better data and more robust fermentation technology. Join us on Biomanufacturing and Fermentation Technology by Prasad Ornala for our upcoming series featuring lead researchers and process engineers. We're discussing everything from bioreactor design to downstream processing, DSP efficiency. Follow us now to join the conversation on the technical frontiers of biology.